Welcome back to another video. We are talking about hypothesis tests here. This is part 3 of section 7.1, where we are going over an overview of hypothesis tests. Okay, so just a quick summary of our key terms. We've got hypothesis statements we've got the null hypothesis and the alternative hypothesis. We write those using H0 for the null hypothesis, HA for the alternative hypothesis, or H1 as well. But I like writing HA to remind us of alternative. Okay, so what was the meaning of both of these statements? Well, we set up what we call hypothesis tests, and we've got 3 possible types, right? We don't do all 3 at the same time. We pick one, okay? And the idea is we always start with the null hypothesis. So the null hypothesis for all 3 situations is exactly the same, where we're saying whatever the parameter that we're studying, okay, could it be proportion or it could be a mean? We say that it equals to a number. What's that number? Well, it's the number of an old parameter. Okay, that's why I call it the past parameter. Okay, so this is our basic assumption, right? Until we collect new information, the idea of the null hypothesis is basically status quo, right? We assume right now it's the same as what it used to be, unless we have new information to change our minds. So we change our minds, essentially, we're going to test whether to change our minds with the alternative hypotheses, right? And we've got 3 types here, where we've got a left-tailed test means that the parameter is smaller than the number from the past, okay? A two-tailed test means that the parameter is not equal to the number from the past. Okay, and remember what that means. It doesn't mean that it's mathematically different. It means that it's different by a lot. In statistics, we say it's different by a statistically significant margin. This is what that means, right? The middle of the line is the number from the past. To be considered different, we have to be in those pink extreme tails, right? That's what it means to be statistically significant. So we can be different by a little bit left and right, but we will change our minds only if it's not different by a little, but different by a lot. Okay, and finally, right tail test means that the parameter, we think it got bigger. Okay, so that was essentially the different types of statements. What's next? So when we make our conclusions, right, there's going to be 2 possibilities. Either the statistical evidence from the new sample tells us that our sample is coming from the pink part, right? So let me draw a little big dot over here. That means that there is enough statistical evidence to support the claim that HA, whatever we wrote as our statement for the alternative hypothesis, we have evidence that basically the new parameter is different, either smaller, bigger, or larger. Okay, the other possibility is, well, maybe our sample comes from the green part. If it comes from the green part, means that our sample is telling us it's not different enough by a statistical margin for us to change our minds. So what we say is there is not enough statistical evidence to support the claim that blank for the alternative hypothesis. So notice how it's kind of curious how we are choosing to write our sentences here. Both sentences are basically supporting the alternative or not supporting the alternative. We actually never really reference the null hypothesis. Okay, so the big key terms, maybe I should say one more time here, is the standard notation we're going to say is in type 1, we say we reject the null hypothesis. Okay, and what that means, rejecting the null hypothesis means that we support the alternative. Okay, and this is essentially the changing our minds. The other possibility is we failed to reject the null hypothesis. And I like to summarize this again. So that means we don't support the alternative hypothesis. Okay. You're going to hear me also say in this situation that we keep the null hypothesis because it is a little bit weird to keep track of the double negative. Very British. Okay, let's jump to my favorite example in this section. Okay, so this is essentially a logical exercise where there's actually 4 outcomes that can occur when we do a hypothesis test. Okay, and after we finish this example, we'll talk about COVID tests. So if you lived through COVID, you'll know what I'm talking about when we get there. But first, what we're going to start off with is the following question. Okay, again, it's more of a logic puzzle than a hypothesis test, but let's start off with the question, is there poison in the well? Okay, so pretend that, this is some green grass. This is where your castle lives. And then, of course, you need drinking water. So you bury deep into the ground until you reach some groundwater. Okay, and you got to think back to medieval times here where if 2 different kingdoms are fighting, it would be common to do what's called a siege, where you would basically for the people in the castle, they would be stuck there. Sieging a castle means that you put your army surrounding it so that nobody can leave. Okay, and another common tactic was basically they would poison wells, so this is where this example comes from. Okay, so what is the logical setup for our hypothesis test? So here is our HT. So to run a hypothesis test, we always state what the null hypothesis is. So here is our null hypothesis. Of course, we should assume that there is no poison in the well. This is what would be the normal situation. Our alternative hypothesis is going to be that there is poison in the well. Okay, so what happens now is there's 2 things going on. One is what we call the truth about the population, or just I call it the reality side. Okay, and in reality, there either is poison in the well or there's not poison in the well. But again, I want to phrase this from the point of view of the null hypothesis. So there's either 2 possibilities in reality. H0 is true or H0 is false. So let's write what that means, right? So when refers to reality. So what is reality when H0 is true? So essentially what we've got is we've got this kind of column of information. So we've got H0 is true, H0 is false. Okay, and let's write this stuff in here. So if H0 is true, what does that mean? We go over here. H0 is that there's no poison in the well. So we're going to say that there is no poison in the well. Okay. When H0 is false, that means that this is actually not true. That means if it's not true that there's no poison in the well, that means that there is poison in the well. Okay, again, those are the 2 possibilities representing reality. So what's next? What's next is let's look at the following, which is the conclusion. Okay, this is the decision that we're going to make based off of our sample, right? This is a conclusion. What I really want to emphasize here is this is the conclusion based off of a sample, okay? So what do? Well, we get a bucket. There's my bucket. You send it down the well so that you fill it up with water. This is going to represent our sample, okay? And then we have this person's sad because they are basically in task of having to drink the water to test whether there's poison in it. And based off of whether this person gets sick or not, this is how we will make our conclusion based off of our sample. Okay. So if you want, yeah, so two possibilities based off of the sample. Okay. One possibility is we do not reject the null hypothesis. I'm doing this in green because think of this as, again, fail to reject means we are essentially keep the null hypothesis. So if we keep the null hypothesis, that means we have that our conclusion based off of the sample is no poison in the well. And in fact, I'm going to color code this one green since, again, no poison in the well is good. Okay, now, in this situation, I'm going to color this first box in this corner green because this is a good situation, right? Reality is that there's no poison. We get a sample, a bucket of water, and test it, and based off of that test, there is no poison. So reality matches our conclusion based off of our sample. This is a good situation. We are happy. So I like putting a little happy face here. Okay. Let's be clear about what I'm saying about being happy. What we're happy about is that our conclusion, our decision based off on our sample matches reality. Okay. Of course, in this same top row here, right, if we are in the fail to reject zone, still over here, there is no poison in the well. So excuse while I copy over here. Right, our conclusion is that there's no poison in the well. But what if in reality H0 was false where there was poison in the well? This can happen, right? This is one of the things that we have to be aware of when we collect a sample, even a random sample, right? It's still just a collection from some of the data. So basically, maybe that whatever the poison is, it wasn't very well distributed. So, for this one specific bucket, there was no poison just from that one sample. Okay, now I think this is not very good. So I'm going to make it pink over here because I think when we've got that reality, there is poison, does not match the conclusion, no poison, we should not be very happy. Now, I'm going to hold off on my sad face for a little bit, but I'll make it pink to refer that, okay, they're not matching, which is inconsistent. Okay, what else? Again, please excuse my copy pasting here. So remember, in this first column where H0 is true, that means this is reality. So I'm going to put this down here, that there is no poison in the well. Let's get rid of that happy face. Okay, let me also copy the reality from the other column. Okay, remember this is reality here. So reality means when there is poison in the well. I'm going to put that down here. Okay, so now what I want to do is, now let's look at our decision based off of our conclusion. This time we reject the null hypothesis. Okay, remember this means we support the alternative when we reject the null. What does that mean? If we support the alternative, that means that there is poison in the well. Okay, and that is the conclusion based off of our sample. So since this is the same conclusion on both of these rows, again, you're kind of thinking about the row based off of the reject. That's why the conclusions here are exactly the same. Okay, so let's think about what is happening here. Okay, in this situation, reality is telling us that there's no poison, but when we send down the bucket and we get it, that the person who has to test this actually gets sick. So we think, based off of that sample, that there is poison in the well. Of course, reality doesn't match the conclusion. Now, of course, there could be a number of factors for why this is true, right? Maybe the person just got sick from the cold for some completely other reason. Maybe they ate bad food earlier in the week and they just so happened to get sick right after they drank this water. Okay, so there's all sorts of other reasons that could have caused it. Okay, I think we should put pink here because, again, reality does not match the conclusion based off of the sample. So pink means we should not be happy in these two corners over here. Okay, finally, let's look at this situation over here. Okay, and remember, I want us to separate the content of the test versus whether we're happy with our decision. Okay, so here we are happy with our decision because reality tells us that there is poison. Our sample, our sample bucket of water here, our person tests it and they do get sick, making us to conclude that there is poison in the well. Okay, now I'm going to say that we should be happy here, not because our person got sick from the water, because we are happy that the sample and the reality match. Okay, so I think we should draw another happy face here. Okay, and again, let me be clear. I'm not happy there's poison in the well. What I'm happy about is that our sample that we collected led us to the correct conclusion. So if you think about this from like a, public safety point of view, this is good, right? If you know there's poison in the well, you close down the well and nobody is going to get sick. Okay, and this is a good success. I mean, it's good in the sense that you're going to use this information to help people make a good decision. All right, now let's go back to the two times where they were inconsistent, right? So I am going to have us think about for a second. I'll draw them in red because I'm going to draw sad faces. So I'm just drawing the little eyeballs for now. Okay, let's think through which one is worse. Okay, there is no poison in the well, meaning the water's fine, but our conclusion means that there is no poison. Okay, so in that situation, we would close down the well because we think it's poisoned, but it's not. Oops, I'm sorry. Okay, that's not good, but nobody would really get sick from that. So I'm just going to put a sad face because, again, our conclusion does not match reality, but it's not as bad as the other possibility, right? The other possibility is over here where, okay, reality is there is poison in the well. It's poisoned. But we conclude based off of our sample that there is no poison, so we think the water's perfectly fine. So people start drinking it, and lots of people get sick now. This is not a good situation. So what I am going to draw is, I always like to draw even a really grumpy face, right? Because we think this is worse. Okay, and this is bad. Bad from the point of view that reality doesn't match our conclusion. But that is true for both of the pink squares here. But of course, the top one is even worse. Okay. Now, I want to highlight this important note down here where it says we never prove that there's no poison in the well, right? This is one of those things that we just have to be very cognizant of, very aware of when we're doing statistics, right? We're never proving anything. We're either again, we're basing our decisions on a sample. That's a small amount from the total. So we have to live with the possibility of making errors. Okay, and again, we never prove anything. We either find evidence to support or not support something. So, with that in mind, this leads very naturally to the next key term. These are called types of errors. And what I like to do is I like to draw this table, and I call this one a type, well, I don't, but we call this a type 1 error. And we call this a type 2 error. Okay, the thinking is, okay, we give everything names and statistics. That's one thing. The second thing is 2 is worse in this situation. Okay, so I've got the more formal definition down here. What is a type 1 error? So technically, we are saying that a type 1 error is the mistake of rejecting the null hypothesis when it's actually true. That's the situation, right? Actually means reality is that the null is true and that we rejected the null. Okay, so that's a type 1 error. The symbol that we use for that is alpha. So remember the little fish? Well, here is the true meaning of the little fish. Sorry, even though it's an error, my little fish has to be happy because it's cute. All right, so alpha is actually the following probability. It's the probability of rejecting the null hypothesis when it is actually true. Okay, and how do I know that? Well, it's right here in the symbols here. This means probability. Okay, and I've got parentheses and I've got this. Remember that slash notation we translate to such that, or I'm sorry, given that. Remember this was the conditional probability. So we're saying the probability that we reject the null, given that in reality the null hypothesis is true. Okay, so that is the technical term of alpha. Thankfully, you don't really need to remember this formula here. You just need to remember alpha is the probability of a type 1 error. Okay, there's also the type 2 errors. Okay, and this is the mistake of failing to reject the null hypothesis when it is actually false. Okay, when it is actually false means we are looking over here. And what is it that we're doing? We are failing to reject when it is false, meaning we keep it when it's false. Okay, so that is a type 2 error. Oops. Next up is the symbol that we use. I'm not going to highlight it. I mean, it's down here, but I'm not going to highlight it because we don't really need it. But it's beta is usually what we use to represent the probability of making a type 2 error. And just like alpha, we can use probability notation to kind of write this more succinctly. Beta is the probability that we failed to reject H0, given that H0 was actually false. And you can see that logically, the two sides of the given that are incompatible, and this is what we mean by making an error. And here I rephrased it using the word mistake. Okay, so that's type 1 and type 2 errors. This is one of my favorite examples. Again, what we could do for every single hypothesis test is write down the types of errors. But I think this example is really excellent. Another example that's fantastic, I believe this is in the homework, is going through the justice system, right? We say a defendant is not guilty until proven otherwise, right? So they can be, basically we start off with the null hypothesis that they're not guilty, and then you have to find statistical evidence, meaning overwhelming evidence that they are guilty. Okay, so it's kind of basically a hypothesis test. Okay, so what is next? So we're almost done with the section. So let's go ahead and finish things off here. Let's talk about majorities. So majorities, let me put a GTQ by this because this is kind of, it's going to come up from time to time on the homework. So a majority just means for us a percentage equaling more than 50% of the total. Okay, so that is our key term for a majority. It's just more than 50% of the total. Okay, to test a claim, so this is code word for if we are going to run a hypothesis test, if we're testing a claim about a majority, we are going to say that the null hypothesis is going to be, well, again, since percentages and proportions, we use these interchangeably, we're going to use little p, and we're going to convert the 50% to its decimal form of 0.50. Okay, so this is going to be our null hypothesis. So let me put this over here. The hypothesis test for majority, they are always going to look exactly like this. So H0 is going to be little p for proportion equals 0.50. And again, we will always choose these exact numbers for a majority. So what does it mean to have the alternative hypothesis? Well, it makes sense. Oops, sorry, my color coding got off here. My alternative hypothesis, that means little p. Okay, so to be a majority, there's only one choice for the type of test we should do, right? A majority means that p is greater than 0.50. And this is where it gets kind of interesting, right? So first, let me just box this, since this is pretty helpful and important to remember. Let me make a note that this is going to be a right-tailed test always. Okay, and now let's kind of think through the logic real quick, right? So what we're saying with a test like this is, let's imagine we've got a bell-shaped curve. We've got the sampling distribution of all possible proportions. We are saying that we believe it's 0.5 is where the middle should be. And what we're looking for is we're looking for statistical evidence that we are far away from the middle. Okay, so what that means is we are looking for this right tail over here. Okay, and we have to be far, far away than 0.50. Okay, so of course, as we've talked about earlier, we need to figure out where that cutoff is. We call those cutoffs critical values. Okay, and then again, so actually, statistically speaking, having evidence for a majority means not only is it 0.50, but it has to be much, much bigger, right? So again, like let's say like 60%. That's much further away than 50% or maybe 80%. Okay, that's what a majority means statistically speaking. Okay, let's look at this example here. A Gallup survey reports that 57%. Okay, and right off the bat, the other word that is important here is survey. This is code for our sample evidence. Actually, hold on. Let me think about this for a second. Let me just read it first. A Gallup survey reports that 50% of 504 randomly selected gun owners support stricter gun laws. Test the claim that a majority of gun owners favor stricter gun laws. Write out the hypotheses for this example. What would a type 2 error be in this scenario? Okay, well, I was correct actually in that in this problem, they don't give us past information. This, I'm going to rechange the color. This is a survey. This is a sample. So basically, this is code for our sample evidence. And this is p hat 0.57. Because remember, we always work with the decimal form. Okay, what else do they tell us? Well, they also tell us that this 504 represents little n. Okay, and again, that's from the survey, right? Okay, so test the claim This is code for run a hypothesis test. The other keyword here is majority of gun owners who favor stricter gun laws. Okay, so this is secretly the claim. So it looks very similar to what we were practicing with confidence intervals. The difference is what we're not going to do, right? So basically chapter 6, let me just do a quick little review here, right? Chapter 6, what was the goal? It was to estimate in this case, proportion, right? So what did we do? Well, we took the 57% and then we subtracted the margin of error and then we added the margin of error. I'm not going to calculate it. I mean, you probably remember how to do it, but and then this would give us basically a range of values where we think the real proportion of people who favor stricter gun laws would be. Okay, that was last chapter. What we're doing in this chapter is very different. We're not trying to estimate the proportion. What we are trying to do is test the claim whether a majority favors. So it's very different. Okay, now, I suppose since I have it written here, because it's exactly the same for every majority question, these are going to be the hypotheses. Since I ask right at the hypotheses, here we are. It looks just like this. Okay, and it does ask what is the type 2 error. Okay, so for the type 2 error, what I really like to do is I actually like to make this little table very quickly where I put the 2 here, the 1 here, and usually I put little happy faces to represent we did not make an error here. And then we have to remember what goes on top. Okay, I'll help us out here. We've got reality on top, H0 true, H0 false. And then on the side here, we've got the conclusion based off of our sample. And we've got the fail to reject. Okay, and I'm going to start using this abbreviation. I know it's kind of small. FTR, fail to reject, H0. And then we've got reject, H0. Since we want type 2, okay, what is a type 2 error? Okay, so basically, let me convert this little table into words here. Let's first start symbolically. A type 2 error means that we conclude fail to reject when in reality H0 is false. So basically, okay, so this is what we need to do now. We need to take this and turn it into a sentence. Okay, here we go. A type 2 error is we conclude. Okay, what does it mean to fail to reject? Fail to reject means we keep the null hypothesis. So let's write down what the symbols P equals 50. So we conclude that the percentage of gun owners that favor stricter gun laws is 50%, when in reality it is, okay, H0 is false, means that we basically have HA is true, when in reality it is greater than 50%. Okay, that is our nice little sentence here, and you can kind of turn this into a template here, where let me underline the pieces that would change. Okay, that part that I underlined would be different depending on the problem. Here we're doing a proportion and we're doing a majority question. That's why the underlined piece reads the way it does. But then we say when in reality it is blank. Okay, and then we write the alternative hypothesis. Okay, good. That is a good example to just practice the type 1 errors. I think that the most difficult thing in this entire chapter is actually identifying the type 1 and the type 2 errors. So some students can just do this really easily, but I think most people actually find this quite hard. So if you're kind of thinking like, whoa, this stuff is really hard, it is, first of all, but just know that it's just kind of isolated to this section. You can still do really, really well on this chapter if you just kind of ignore how to solve this. Of course, it's nice if you understand what we did in the video, and understanding the video, I would say, is probably more important to me. Okay, let's wrap up. We are almost done, so I think I'm just going to take us to the finish line here. Okay, last thing to talk about is level of significance. So this is an important key term here. So let me put GTQ, mostly just to know this term. And what is this? So we will not know 100% if our conclusion of our hypothesis test is correct. But we can assign a probability to making a type 1 and type 2 error when we complete a hypothesis test. This is essentially the meaning of little alpha. So the level of significance is going to be our brand new name for the little fish. So remember, when we did confidence intervals, little alpha, we just kind of introduced it as a symbol. The meaning, of course, is the same, where it's the probability of the tails. Okay, but when we do hypothesis tests, it takes on the meaning of making a type 1 error. So it's the probability of making a type 1 error. Okay, and since we went over this stuff earlier, let me just fill in the blanks here. In other words, when we take a sample that makes H0 look wrong, but when it's actually true. So the symbols are, let me just think real quick. Alpha is when we reject the null hypothesis, when in reality the null hypothesis is true. Okay, I hope I got that correct. Oh, perfect. Okay. Fact. Quick fact here. As you blank the probability of one error, then the probability of the other error blank. So let's say type 1 errors, I don't want to make an error, right? So what if we want to decrease the probability of one error? Unfortunately, what happens is the other type of error increases. So basically, what we have to do is you just, depending on the situation, depending on the field of study, everybody kind of decides off where they feel comfortable with the type 1 and type 2 error probabilities. Picking these is way beyond the course, like way beyond what we are going to study. I just want you to be aware of where this lies in statistics. So basically, the next thing is, now that we know what level of significance is, how do we choose a significance level? Well, remember that symbol for that is alpha. We're just going to say it's between 0.01 in our class and 0.10. Okay, remember that means 1% and 10%. So again, every problem that I will tell you will always have a level of significance somewhere between 0.01 and 0.10. So this is basically the range that's most common. So if I don't tell you a level of significance, basically we are going to assume it's exactly in the middle here, which notice this is 5%. So this is that magical number in statistics, right? 5%. Again, the other part means 95%. This is the middle 95% of a bell-shaped curve. Let me keep drawing. I keep drawing this because it's kind of the most important part to understand, right? So alpha is the probability outside of the middle. And again, we're going to kind of change this up a little bit as we progress, but that's the idea here. So I guess memorize the following fact. Use alpha is 0.05, which corresponds to 5%, if the level of significance is not given. Okay, so this is going to be an important thing to just kind of keep in mind, and I'll remind you of this every single section. But again, usually the problems will tell them to you at the beginning, and then as we get more advanced, some of them might leave it out. If they leave it out, now you know what to do. You use that 5% as our cutoff. Okay, so we are done with 7.1. All of this is cool, but I will skip this, which means I will not test you on this information. So thank you so much for watching these videos. I'll see you in class. Have a great day.